So today, I'm going to challenge you that if you can answer this question, you have a deep and fundamental understanding of statistics. I'm going to draw one thing on the board, and I'm going to draw it, you know me and writing on these whiteboards. That's a square, by the way, and it has a length L. It's the length of one of the sides are L. It's a square, so all the sides are L. If you can answer this question, you fundamentally understand statistics. And I challenge you with that one today. By the end, let's see if I was right. What is the area of this square? L squared. The area of my square equal L squared. Okay, you get three credits. You can go home. I tell you, it's that simple. Okay, I'll make it, and I'll just build from here. And you know, the only other shape that I want you to tell me if that is base, and that is height, and that's now a rectangle, by the way. What's the area of the rectangle? Base times height. Cool? All right, so you can calculate area. It's not a problem for you. Okay, not for 6002, but let's just stretch you a little bit. What about that triangle? Half of the base times the height, okay? What about the circle? Oh, boy. Pi r squared. Okay, okay, okay. What's that one? What's the area of that thing? More difficult, isn't it? Can you remember from school maybe how to do that? If this was a function, what kind of math would you use to do that? What kind of calculus? Area under a curve, what is that? An integral, great stuff. I tell you, now you're already at numerical methods. You can now do mathematical statistics if you go that far. Okay, so I'm going to claim if you can do that, if you can think of area, you can do statistics. Okay. The other thing that we're going to talk about today, which is of great importance to us, is this uppercase X. And we're going to call that a random variable. So remember before I said we loosely use this term variable. That's the name that goes on the top of every column in the spreadsheet. That's age, that's blood pressure, whatever the case might be. I just called that variable, and there's a name for that variable. We called that one age. We called that one, and we had long form, tidy data, variables, subjects. Remember all of that? Okay. But now I'm going to be slightly more sophisticated, and I'm going to call something a random variable. So don't think of the name that goes on top of the column anymore. That's not what you're talking about. When we talk about a random variable, we're going to talk about a function that spits out a number. And this function, let's think about it. Let's look at my function. My function is walking, walking, walking straight to you. My function asks you, what can I ask you nicely about yourself? What's your favorite color? Black. Black. Okay. And I can assign a number to black. Let's make it a RGB number that's 000000. Okay? Now look at what happened. I performed an action, and out popped a number. Okay? So that's what we think about. It's a function, and that function might just be me getting 50 people at random from a population, and I measure each of their blood pressures. Okay, I did some action, there's some function, and out popped a random value. But in essence, if I pick some of you at random and get your blood pressures, those numbers that I have there, that happened at random. Okay, so just think of it as slightly more, it's obviously more sophisticated than that, but let's just think of that as a function. It is something, some function, remember from school, f of little x equals x squared, a function of x. Okay, I do something, I pop in something, and the function will pop out a number. If I pop in 3, the first thing pops out a 9. Okay, you can think of that. It's a function, it's some random, function that produces a number for me. So if I just walk around and I asked everyone what is their favorite color, and we just stick to some predefined, what would I call that? A universal set, remember? Sample space. And we can only pick from that. I can now count how many people chose black, how many people chose orange, how many people, and I can count. You know, maybe there was 21 of those, there were only 17 of those, etc. I can count, okay? That would also be a random variable. We went and we got this data and we said, let's count everything. So I can now look at the probability amongst all of these of, that you would choose black. What would we say the other word for probability was? Proportion. Okay, probability, proportion, exactly the same thing. Think back to the area of a rectangle, base times height. Just think back to it. I'm going to go back there again. So imagine in the end there were 100 people. What was the probability of black? Well, it's just a fraction of the whole. Probability proportion is always going to be a fraction of the whole. You've got to know that. So it's going to be 0.21, 21%. But I can also say, well, this thing that it can possibly be, I can call that a random variable, x. And I can say, what's the probability that x equals black? I'm just expanding my notation here. And it's still going to be 21 over 100. Can everyone see that? It's a proportion of a whole, a probability or proportion of a whole. Okay, but I'm just slightly more sophisticated now. I'm going to say, what's the probability that this random variable is equal to black? Well, from my data, it seems it's 21%. Anyone see that? See how statistics works. It's always this proportion of some whole. Okay, so everyone's got that. This idea, just you don't have to have a full concept of it now. This is not mathematical statistics, but we have this random thing, and we're always going to call it x. Okay, and so let's have this random thing x, and it's very nice because x, we find x in mathematics, which means statistics can be based on, we can do some math with this thing. And so we have this variable x. And let's assume that we are, what can we do? Let's assume that we are flipping a fair coin. We are flipping a fair coin. What can the outcome be? Heads or tails? Heads or tails? Theoretically, if it's a fair coin, what's the probability of a heads? It's 50%, 0.5. What's the probability of tails? Don't say 0.5, say 1 minus the probability of heads. Remember the complement rule? Okay. So because there's just two outcomes, it's got to sum to 1. So the probability of heads plus the probability of tails has to equal to 1. So that you can always think of the other one as this 1 minus this one. Because if this was not a fair coin and this was 0.3, I did not have to tell you what the 0.7 was. I could just say this one's 0.3 and you'll know the probability of that one would be 1 minus the probability of this one. 1 minus 0.3 is 0.7. Everyone happy with that? Just some simple sort of things to think. So I can now also say, what is the probability, and maybe x is, I've just got to describe in words what x is in every case that I use it. What's the probability that x equals heads? Oops, heads. Can you see x? We can just use it. That's how we use a random variable. It's this thing that can take on a random value, okay? And what is this? We all said that that's a half. Now, this is very easy because I can write a little table. I can say, what's the probability that x equals heads? Why do I forget the a all the time? That's a half. And the probability that x equals tails, well, I said that's 1 minus the probability of that, but let's just say that. Okay, so I can write out a nice little table. What if I roll a fair six-sided die? Can I make the same little thing? X is now the value that lands face up. Can you see x? Okay. Again, what is the sample space, the universal set? 1, 2, 3, 4, 5, 6. So we're going to say the probability that x equals 1, the probability that x equals 2, all the way down to the probability that x equals 6. If this is a fair coin, what is this, each one of these going to be? 1/6. Okay. Now let's name this thing that we've just written on the board. Just name this thing that we've written on the board. We have written this whole table. Okay, we have values, and I'm going to give it a name. And this name you have to write down because you've got to know it. I'm going to call this a probability. This is a probability mass function. Probability mass function. Okay. We use the term mass. You might have seen in a textbook probability density function, but we distinguish the two words. Sometimes we can use the word mass, sometimes we can use the word density, and I'll say later why we do that. A probability mass function. Okay. You give me a value that little x can take, and I can go to my probability mass function, and you give me the value that x can take. Or if you say, well, what's the probability that x takes on the value 2? I can go in my table. Now, this is very simple. And I can just read off the value. Just as I could at school, take the f of x equals x squared. I can say, what is the value if I plug in 2 there? Well, then I get 4. If I plug in 3, I get 9. Same idea here. A probability mass function. You give me a value that the random variable can take. And this time it's much easier than x squared because I just have 6 possible values here. And I just read off the table what the value can be. Okay. But look at what we've learned now. We've said P for probability or proportion. And we instantly knew there's only 6. And this is one of the 6. So it's some proportion of the whole. We've all got that idea now about statistics. It's this probability or proportion is this some fraction of the whole. But I can also think about the values that I can select from the sample space, and we could say that's a random variable, x equals 1, it can take on a value 2, it can take on a value 6. By the way, in many textbooks you'll see the probability that uppercase x equals little x. Very confusing, but that's what we do. Statistics is how can we confuse people by the words we use and the notation that we use. That's just a little value that it takes in a specific case. Cool? The value, uppercase x, little x is now 2. Okay, but so happens that that's also the uppercase x. But this is the random variable. This thing that can take on certain values, and I can calculate from a probability mass function what is the probability that my random variable can take on that value. So we're just learning a new way to say a very simple and silly thing. It's so, I mean, it's a little bit absurd, but we're just learning the language and how we think and talk about it. Okay, so everyone happy with this idea of a random variable, x, that can take on certain values. So let's make it take on some more fun values. And somewhere along the line, I have to promise to get back to the area of let's make it a rectangle. Let's make the rectangle the thing that we're interested in to start off with. So now, let's think about rolling 2 fair dice. Okay, 6-sided dice, 6-sided dice. Roll dice number 1, roll dice number 2, and what I want to do is add the 2 values that lands face up. A bit more interesting than just rolling it once. I've put on the board for you what can happen, and all I want to do is just add those 2 numbers. Okay, so obviously I can roll a 1 and a 1. Is that fair? What does that sum to? 2. Okay. I can roll a 1 on the first die. By the way, if it's a 1 and a 1 or a 1 and a 1, that's the exact same thing. I can't distinguish between those 2. If I looked away and you changed the 2 around, I'm never going to know this was the 1, that was the 1. 1 is 1. Okay. I roll a 1 on the one die and I roll a 2 on the other die. What do I get? 3. I roll a 2 on this one and a 1 on that one. What do I get? 3. Okay, cool so far. I roll a 2 on this one and a 2 on this one. I get 4. But I could also roll a 1 on this one and a 3 on that one. What do I get? 4. I can roll a 3 on this one and a 1 on that one, and I get 4. Interesting thing going on. There's just one way to get a 2. There seems to be 2 ways to get a 3. There seems to be 3 ways to get a 4. Guess how many ways there are going to be to get a 5? 4. Okay, you know this little one. What's the most common one? 6 ways to get that one. 7. Okay. 7 can be written as 1 plus 6, 6 plus 1, 2 plus 5, 5 plus 2, 3 plus 4, 4 plus 3. Okay, there's 6 ways to get 7. And then 8, it drops down again. And 9, 10, until we get to 12, and there's just one way to get a 12, and that's a 6 and a 6. Okay, how many total possibilities are there? 36. Cool, some of you know that, 36. Can I write a proportion of the whole? Yeah, of course I can. What if my random variable x is, I have to describe it, it is a function that spits out a number, and my function here is rolling a die and adding the two numbers. Adding the two numbers is my function. Okay, instead of it being x squared, it is add two numbers that the dice lands face up. Cool. So this random variable x, what values can it take on? Little x. What can little x be? What's the smallest value that it can take on? What's the largest value that it can take on? 12. Cool. So this one can take on values. It can't take on 1 because I can't roll a 1. Can't take on a 13. Definitely can't take on a 5.5 or 7.365. Okay. So it's going to be 2, 3, 4, 5, 6, 7, 12. Okay. How many ways are there? Probability that x equals 2. What's that going to be? Out of those 36, how many ways can I get it? Only one. One. So that's 1 over 36. What's the probability that x equals 3? 2 over 36. Can you all see that? Can you all see that? Pretty easy. And then I'm going to get to the probability of x equals 7. And that we said is going to be 6 over 36. And then all the way down to probability that x equals 12. And I'm back to 1 over 36. Okay. If I add all of these up, what am I going to get? 36 out of 36, the whole. Okay. Guess what I've just written on the board? If I put pink around it, remember when I put pink around it, what is this thing called? A probability mass function. You give me probability mass function. You give me a value that this random variable can take, and out pops that probability. But you all saw it's actually just a proportion of the whole. There's nothing special about this thing called the probability. Also, what's the probability it's going to rain tomorrow? Well, somewhere along the line, they run multiple simulations, and they see in how many of those does it actually predict rain tomorrow. And they'll tell you the probability of rain tomorrow. Okay, it's some fraction of a whole. It's always some fraction of a whole. And that's what we have, a probability mass function. Now, I've got to make things slightly more entertaining because, I've got 11 possible values there. And that's still fine, but what if I had 342? It starts getting a bit annoying to write out whole probability mass function. Okay, so what we usually do, we want to visualize this thing. And so one nice way to visualize this is by a bar chart. Cool, data viz, a bar chart. Okay, so a bar chart is just going to be some little rectangle. Oh, rectangle? What was the area of a rectangle? Oh, so why did this guy talk about area of a square to start off with? It's coming back, it's coming back. Okay, I can have little rectangles. And each one of those rectangles, I can think about what the height of that rectangle is. Okay? And we can just make it that the height of the rectangle just so happens to be the probability mass function. What was that? 1 over 36. Cool, so let's make this y-axis. Let's make that exactly 1 over 36. Now here comes the next little one, and its height is 2 over 36. Can you see that? All right, can you see that I've got gaps in between my bars? There's a reason for that, isn't there? So let's do 3 over 36. So by the way, that was of rolling a 2. That was of rolling a 3. That was rolling a 4. Okay. Why does a bar chart have gaps in between? Yes, I want to indicate the fact that 2.3 is not possible. And I do that visually by leaving a gap between the bars. That's opposed to the thing that we'll see later on, which is a histogram, which is also little rectangles, but they touch each other. To indicate visually that there are a range of numbers going on there. It's not just one distinct number. Because it can only take one possible value, we'll say that the base is 1. Now don't get confused because this is exactly 2 and that's exactly 3. That's why the base is 1. That's not so. The base is 1 because it's just one unit of value. It's just 1. And we have a very specific name for this. We call it a discrete random variable. Discrete random variable. That does not mean it's shy in some way. In a way, discrete. Okay, It just means it can only take certain possible values. In between those, these are numbers. Remember when we spoke about measures of levels of measurement, we said that nominal and ordinal variables, especially ordinal, we can give a number to it. How much pain do you have between 0 and 10? Those are not real numbers. Here we're talking about the kind of random variable. It's discrete or it's continuous, but they are both numbers. Now, when I asked, what's your favorite color? And most people chose black, and we'd say, well, there were 21 people who chose black. That's a number. The black itself, its level of measurement is nominal categorical, which is not a number. But as soon as I start counting them, I've performed some function counting how many people said black, and I can express a number. So these things are always numbers. Even though the thing I'm counting, its level of measurement was not numerical. Cool? See that distinction? So people often get that confused. Give me the levels of measurement, and then they go discrete, continuous. No, 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 no. That's nominal, that's numerical and categorical. But as soon as I take, the numerical ones are obviously real numbers, but as soon as I have categorical, I can count how many each of those occur. Now I'm back to a number. And because I selected you at random, and 20 of you said black, that X is a random variable because it might as well have been 20 or 19 or 34 of you who chose black. That's random. It's a random value. Just counting how many there were. Can you see the distinction between this? So we always can say discrete random variable. And as soon as we talk about discrete, we mean this possible value that little x can take, so x equals little x, is a discrete value. I cannot have it 2.5. These are numbers. I cannot have it 2.5. I cannot have 3.48. Okay? And worst of all, there is a universal set, so I cannot have -1 and I cannot have 24 when it comes to adding these two dice. Okay. Cool, everyone's happy with that? Very simple stuff, but very powerful. And so discrete, we put a little gap in because I can only have these discrete values. And another thing that we say is when we talk about all the possible values that it can take, we say probability mass function. Whenever we talk about discrete random variables, we're going to say mass function. We're going to use the word mass. Okay, probability mass function. So here's my bar chart. And now, so let me show you one that I've already created because I kind of want to draw all those rectangles. Something magical is going to happen. Do I have it here? Let's see. There's my little bar chart. So there's my values, 2, 3, 4, 5, 6, 12. Can you see that that thing forms, visually it's very nice to see. If I had 200 possible values and I just wrote them all out, 23 over 212, 14 over 212, that becomes very long. Okay, visually it's nicer to look at. Can you see there's a pattern there, a visual pattern? And I'm going to use this pattern, I'm going to abuse this term pattern for the idea of a distribution. So can you see I had my probability mass function where I just wrote it out. Probability that x equals 2, probability that x equals 3, probability that x, and I wrote this all down, all the numbers. Can you see that that probability mass function is now just the image? Okay. But I can make it so that the bases are 1, it's discrete, and the height is just the probability. Now what does that tell us? What is base times height? The area of a rectangle, isn't it? So can you see that I can visualize the probability as the area of a geometric object? Isn't that beautiful? Just think about it. This is crucial. I can visualize the probability of something or the proportion of something as the area of a physical object. There is a square, and because the base is 1 and the height is exactly 1 over 36, 2 over 36, 7 is 6 over 36, and then all the way back to 1 over 36. Can you see 1 times 1 over 36 equals 1 over 36? The area of a rectangle equals the probability of me rolling a 2. Can you see that? Who cannot see that? Because this is just like fundamental. I'm sorry that it's so silly. Can you all see that? Truly in your heart, you can see that. I can represent the probability of the outcome of an experiment as the area of a rectangle. You give me a physical shape, I can calculate the area of that shape, and somehow I can call that that's the probability of something happening. So what's the probability that I roll a 7? Base times height of that rectangle. Okay, what is the area if I sum up all those rectangles? What is their total area? 1. It's the whole. 1 over 36 plus 2 over 36 plus 7 over 36 plus 6 plus 5 plus 4. If I add all of them up, I get 36 over 36. So look at this also. This is crucial. I can say everything that's possible, that can possibly happen, all of it, 100% of what can possibly happen can be represented as an area of 1. And all the individual parts is a little individual rectangle, making up the sum of the whole. But this is so crucial. Every time you read a journal article, you see a p-value. What's the p-value? Was it significant or not? That p-value is an area, a fraction of a whole. Now, this is very easy because it's just little rectangles. But remember, I drew you that squiggly line, and then we thought, well, now we need integral calculus to calculate the area. No matter, you can always think of probability as some area of some little shape. Is everyone happy with that? That's crucial. If you get that, you get statistics. Done. Somehow I can visualize this as an area under a curve. Now, I have to think about one little complication, and that is if I give you 2 dice and I ask you to roll them 100 times, I give it to you and I ask you to roll it 100 times. Out of that 100 times, are you going to get 1 over 36 times a 2, 2 out of 36 times a 3, or is it going to be a little bit more all over the show? Naturally, you feel it's going to be, if you only to roll the 2 dice 100 times, that's going to be a little bit all over the show. So let's just visualize that. I think I've got some visualization of it here. Let's run that first one. So don't worry about this code. So there's my same little thing. I just didn't put all the things on. And there's another little function I wrote to give me this. I've only rolled the die 10 times. This is just a simulation. So I've rolled the die so many times, and on the left-hand side, I'm not doing the proportion of the whole. So that first one was 15, 16, 17 out of a, how many times did I roll this? 100 times. So I rolled the 2 dice 100 times, simulating that, adding it, and I got 17 2s, I got 10 3s, so I'm just saying the frequency of it. I'm not dividing by 100, because then I'll get proportions, okay? So there's absolute frequency. So you can see this one doesn't look like that one. From 100 rolls at random, I got this. So let's roll a bit more. I think I increased these in increments of 10. So I'm starting at 100 rolls, and I'm going up in steps of 10. So I can just do that little thing there and just start increasing. Now I'm rolling 110 times, and that's what I get. And now 120 times, that's what I get, that's what I get, that's what I get. And I can just drag the slider, and I'm rolling it, rolling it, rolling it. There at the end, I've rolled this pair of dice 1,000 times. But can you see I'm still not there at random? How many times would I have to roll so that this one starts looking like that one? How many times would I have to do that? What? Okay, that's a good guess. Okay, but that's not how it works. These things, these probability mass functions, they are theoretical probability functions. Okay, we are assuming at infinity we will get to that theoretical thing. Okay, if we were to do this an infinite number of times, I roll those 2 dice an infinite number of times, I would get to that thing. So we have this idealized version of the world in our models. We are going to have what we call models, and we're saying this model is what produced our outcome. There's a model in the universe for rolling 2 dice that absolutely determines what my outcome is going to look like. But that idealized version, that model, assumes that I could do this an infinite number of times. So these theoretical distributions that we talk about always, you all know the bell-shaped curve of the normal distribution, which we will do today. That is a model of the world. And if I say, well, everyone's height is normally distributed, that's a model of the world. So if I were to take random people, it's that model that is going to describe what I'm going to get. It is in charge of, it determines these values that I can get. most people are going to be of this height, and I'm going to get fewer and fewer and fewer shorter people, and I'm going to get fewer and fewer and fewer tall people. There's some model that determines the possible outcomes that I can get. But those models, those distributions, and they've all got names, because if you want to become famous, come up with a new model, a pattern of distributions, and you can put your name to it. So that's the idealized thing. We say that model manages what we can see. But can you see, if I only do it a couple of times, and this was 1,000 times, I'm not going to get there. And that's a beautiful lesson to learn. You've all read some article and they took 30 people. Or even they did a poll of who's going to win the next election, and that poll people phoned 2,000 people at random. Is that all 300 million? Oh, not all 300 million people can vote. Okay, but that's just a small little subset of. Is that going to look exactly like the whole vote is going to look like in November? No. Okay, I can't get there. Then I would have to do everyone. And so that's a crucial thing. We are never going to get to that idealized thing. Ours are always going to be a little bit different. But if we do this in the right way, we can get close to that. But you can see in this very simple example, even at 1,000, I can't get anywhere near the theoretical probability mass function. Mine still looks horrible. I would have to do many more to get close to the theoretical thing. Anyone see that? Everyone happy with that? Okay, so let's have some fun with these things. Do I have one nice one here? Let's go back. Yeah, I think I do. Let's just see. Yeah, let's have some fun with it. Now, in that first one, I'm asking, what is the probability? We now know this theoretical thing, that this model of the world that determines how dice come out. If I roll them twice and I add the face value face up, we know theoretically what we should get. Okay? We've all seen that I can create a probability mass function. I just have to write out all 11 values. Okay? And we can say, well, let's also create a visualization of that and making the height of the bar that proportion of the whole. And so I can take the area of each of those rectangles and I can think of it as a probability of something happening. So I could ask you, what's the probability driven by this theoretical model of rolling two dice that I should roll a double ones? And you can look at my chart and you can see, okay, I colored that area in red, and the height of that base of that bar is 1. The height of that bar is 1 over 36. What is 1 divided by 36? Check quickly. 0.016. 1, yeah, is it? Yeah. 0.016, something there. Okay, there you go. You all divide, so you can multiply that by 100, get your percentage. But can you see that that comes from an area of a rectangle? I can now ask you the question, from this theoretical model of the world of rolling two dice, what's the probability that I roll a 10 or more? Can you calculate that? Yes, it's the area of those little 3 red triangles, isn't it? So that's 1 over 36 plus 2 over 36 plus 3 over 36. 3, 4, 5, 6. 6 over 36, 1 6, which is? It's a fancy calculator. 1 over 6. 0.166. 16.7%. Can you see that I can just do that? I can draw this line and look at all those values on that side, and my theoretical model of the world, the universe of rolling two dice, I can look at that red area, and that red area gives me the probability that if I give you two dice, we can say, what is it, 16.7%? Yeah. Okay. I give you two dice and I say roll them, and we can all wonder, what is the probability that she's going to roll a 10 or more? Well, it's only 16.7%. We can calculate the probability that something is going to happen from some theoretical model called the probability mass function. Can you all see that? And not only that, I can visualize it like this, which is just areas of little rectangles, and I can even color them in so I can see which part I'm talking about. Can you all see that? This is crucial. This is going to come back so many times. Okay? Happy? Everyone happy with this? So we can really have some fun with that, and we can all think about, if I have something happening in the world and I know what the probability of outcome should look like, there's some model, I can calculate what the probability is that some things might happen by just coloring in a little bit of that area under that curve. And because the whole area of that curve is, and I'm calling it, if I could make a curve out of just a line going through all the tops of this, okay? If I had to have a curve, the area under this curve, which means coloring in all the bars, is 1. You all told me that's the whole. I can think of some fraction of it, as the probability of some outcome. Guess how we calculate p-values? We have a little thing in, we just color a little bit in of it, and we calculate the area of that little bit, and that's a p-value. Okay, I've told you, if you understand the area of a rectangle, you understand statistics. I'm sticking with that story. Okay, so let's have a bit more fun with, there's many of these named distributions. So let's just talk about some discrete random variables. The first one we're going to talk about is the Bernoulli. Famous people, the Bernoullis. Bernoulli discrete probability distribution. Discrete, let me say discrete random variables, so discrete probability distributions. Discrete probability distributions. So a Bernoulli trial, a trial is this, what I said, you roll a die and it lands two faces up and I add them. That was one trial. And there was some outcome to that trial. Okay. So a Bernoulli trial is this thing that you do once and it only has two possible outcomes. So we're back to flipping a coin. Flipping a coin is a Bernoulli random event. Okay. It has a probability of, now, because there's only two things in statistics, what we will do, we will call, it can be high and low, alive and dead, yes and no. As long as there are two possibles. A nominal categorical variable, it has two possible values, two categories, two levels. Okay, we are always going to choose in statistics one of them to be our success, and the other one, by nature, our failure. So maybe it is, someone going to the critical care unit with COVID, are they going to come out the ICU alive or dead? One of the two, depending on how we want to frame our study, alive or dead is going to be the success, one is going to be the failure. And it doesn't have to be, maybe my research question is about those that come out, they died. And that's my success. Okay, so success and failure has nothing to do with the actual word. Okay, but we're always interested in this thing of success. So it's going to be the probability that this thing is a success. And I'm going to give that a probability, and maybe that's the probability is 3. So we would say our random variable is described by, so that squiggly line we read as described by, there's other words for it, there's many words for this thing, follows a, or whatever. We're going to say x follows a Bernoulli distribution if it is this Bernoulli, x follows as if it's Bernoulli, and that Bernoulli distribution depends only on one parameter. And that parameter is p. And that p is the probability of success. Okay, so I can just say, what's the probability that x equals a failure? Well, that's going to be 1 minus p. Okay, if the probability of success was only a third, then the probability of failure is 1 minus the success. Okay, 1 minus a third, 2/3. So that's a Bernoulli trial. It can only have two possible outcomes. I'm going to choose one of them as a success, and the probability that x is that success is little p, and that little p is just this probability of success, such that the probability that x equals failure is 1 minus p. Everyone happy with that? This is some simple algebra. Okay. But now we can have repeated Bernoulli trials. I do one Bernoulli trial after the other. And then we get to the binomial distribution, another discrete distribution we'll talk about. Binomial. So the second one we're going to talk about is binomial. Okay. And we write this following thing. We say x follows a, or is described by a binomial distribution. We usually write bin, and that takes on two parameters, n, p. Okay, but let's be very clear, these trials have to be independent of each other. That's me flipping a fair coin. This, what it lands up now, does not influence at all what the next one is going to be, heads or tails. And even if I had 10 in a row, none of them influence what the next flip is going to be. Okay? So they're independent trials, and furthermore, the probability of the success, so binomial is like lots of Bernoulli trials. Okay? There's only success and failure, and the probability of success must remain the same every time. So they must be independent of each other, and the probability of success has to be constant every time. And if I string those things together, I get the binomial distribution. So the two parameters are n and p. You give me a value for n and p, I can tell you something about this random variable. N is the number of trials, so I flip that coin 50 times, and P is the probability of success. So if you tell me how many trials I'm doing, and what's the probability of success, I can tell you something about the distribution of this thing. So let's have a look at that. Imagine I only do something 4 times. My N is 4. N is 4, and the probability of success is, let's make it 0.4. So I do something, the probability of success, what's the probability of failure? 0.6, okay? And I'm going to do this 4 times. So I do it the first time, and I get a success. Okay? I do it a second time, I get a success. I do it a third time, I get a failure. And I do it well, let's make this 5, because otherwise it's not interesting enough. Let's make this, I'm going to do this 5 times. Makes the math a bit more complicated, but let's go for it. I do it another time, I get F, failure. And I do it a last time, and I get success. Is that valid to happen? I've done it 5 times, and I'm just saying I happen to do it success, success, failure, failure, success. But I know every time I did it, I should have had a probability of success of 40% and a probability of failure of 60%. Irrespective of that, I do my thing 5 times, and that's what I get. What was the probability of that success? 0.4. That one? That one? That one? That one? Can I do some algebra and write it in a different way to save myself some time? Yes, I can say 0.4. How many of those did I have? 3. And the 0.6, how many of those did I have? 2. But I can write it in a different way, 2, can I not? It was the number of cases that I had minus the number of successes. Wait, success is 3. Cool? 2. 5 minus 3 is 2. I had 3 successes and I had 2 failures. I'm just writing it in a different way. Now, you might not remember from last week, but if I have independence, what do I do with probabilities? I get a success and a success and a failure and a failure and a success. What do I do with the probabilities? Multiplication rule. These are independent, so I don't even have to use the general rule, because these are all independent of each other. I can just multiply the probabilities. So I can say 0.4 times 0.4 times 0.6 times 0.6. Where's that calculator? No, don't put it away. I need this. 0.4 times 0.4 times 0.6 times 0.4. Or 0.4 to the power, the number of successes, and 0.6 to the power, the number of failures. What is it? Okay, who's quicker than her calculator? There's another fancy calculator. Don't show me these, and then I'll go buy one. And I'm not allowed to. If I go home with one more calculator, I am sleeping outside.
Okay, I got 0.03456.
It sounds too high.
I got 0.023.
0. Okay, it seems like if I did this independent thing 5 times over, and the probability of success was this specific success, success, failure, failure, success, and I multiply all of those, that's what I would get. Okay, but hang on a moment. Hang on a moment. Well, first of all, before we hang on a moment, let's just write this in a very nice notation. So here goes your professor on his knees. Oh, there we go again. I'm doing this on video so that the authorities can see how bad this ball is. I'm going to say that was the probability of success, yay. And let's say that the number of successes, let's put that as k. So p to the power k. What is the probability of failure? It's 1 minus p in it. And how many failures did I have? Well, the number of trials minus the number of successes. Everyone see that? Everyone happy with that? Just some special notation. Probability of success, probability of failure, to the power, how many successes I had. And failures is just the total number of cases I had minus the number of successes. Obviously, that has to be the number of failures. So it's probability to the power of the successes, probability of failure to the power of the number of failures. Can you all see that? I've just written it very neatly. Okay, and we've done that calculation now. You have to have a look at that calculator of yours. Okay, But hang on a minute. Could I have gotten 3 successes and 2 failures in a different order? Yeah, I could have. I could have had failure, failure, success, success, success. Is that the same as that? Would I have gotten 0.6 times 0.6 times 0.4 times 0.4? Do I get the exact same thing? Yeah. For sure I do. So in how many ways can I have 3 successes and 2 failures? How many different orders of that can I have? Many. Okay, turns out there's a way.
I have a question.
Yeah.
For the probability to the successes,
Mm-hmm.
P to the K, is the probability what had been already the 0.4?
No, I'm just saying, every time I did this, I'll get to that a little bit. What you're saying is, yeah, what do I plug in for those? Yes, my theoretical values.
And then the K would be
whatever we got there. How many successes did we get in our one time?
in our trial.
If I were to do this an infinite number of times, I would get so many successes. Okay, but I've only done it once.
Okay.
Cool question, very cool question. Okay, everyone happy with that? But I'm just saying that I have many ways of getting 3 successes and 2 failures. Okay, and it turns out there's a calculation in the way that we can do that, and here it comes, n factorial divided by k factorial times n minus k factorial. Okay. Let me give you the simplified mathematical version of what a factorial is. So if I have 5 factorial, that equals 5 times 4 times 3 times 2 times 1. Okay, if I had 4 factorial, that would be 4 times 3 times 2 times 1. Simplified version. Okay, everyone happy with the factorial? So in this instance, what is 5 factorial? On the calculators, please. 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. I beat you. So that's 120. Am I right? Arithmetic is bad for me. Math, I love that thing. Okay, what is k? It's the number of successes. So we had 3. 3 factorial is 6. Okay, times n minus k, 5 minus 3 is 2, 2 factorial is 2, okay? 120 divided by 12 equals, is that right? Check the arithmetic. I make no claims that that is correct at all. Don't look at it, okay? My arithmetic is horrible. Okay, so I can count how many ways I could get in 5 trials, in how many ways, in how many orders can I get 3 successes and 3, okay? There's a more succinct way of writing this thing. We just write an n and a k with 2 little parentheses. And out pops eventually this probability that we have some outcome for something that follows a binomial distribution. So we've already seen one probability mass function, this model of the world that determines the outcome of 2 dice. Now we have a new model. We're going to say it's n choose k, n choose k, times p to the power k times 1 minus p to the power n minus k. Okay. We say x follows a binomial distribution with parameters n and p. Now I can work out exactly what is the probability that I get binomial distribution, that I do 5 trials and I get 3 successes. I have a theoretical model of something, if that something can be described by independent trials with the same probability of success. So it's got to be a binary outcome. So where can I use it? We usually say, imagine, and again, sorry, this is my world, you go for some kind of surgery, and we say that the probability of success, and success here means you're going to get a surgical complication. That's my success. And I'm free to say that, that's my research interest. You get a complication from that surgery, or you don't get any complication. So I have a probability of success, and maybe I know from history that 10% of people get this complication after that surgery. Now I can ask the question, what is the probability that I do 36 of these operations, and so what is the probability that I get 4 complications? I can go to this theoretical model that determines the outcome that I should get. What's the probability that I do this procedure 36 times? Next week we've got 36 of these planned in theater. There are 36 of these cases are booked. We know that the probability of success, a complication, is 10%. Can I make plans in my healthcare facility for how many cases should I see to get a complication? If all these things are independent, and we're going to assume that they are, okay, and the probability of that success is the same for every case. Is that so in real life? No, because you've got hypertension, and you've got diabetes, and you are a 21-year-old triathlete, different probabilities of some complication happening following your surgery. Okay, so real life doesn't work like that, but this is an idealized theoretical probability distribution called the binomial distribution, and I can calculate the probability that X takes on a specific value. In this instance, I'm asking what's the probability that X equals 4? I get 4 successes. Well, I know if I can describe this thing by this binomial distribution, I can just plug in all the values, and I get the probability that I would get 4 complications out of 36 cases, given that the probability of a complication in any individual case is only 10%. Okay, is everyone with me? I'm not going to ask you to do the binomial distribution. What I want to bring home is the fact that we have a lot of these distributions. The easiest one we can think of is this theoretical probability mass function of rolling 2 die, and what's the probability of a certain outcome. It's discrete, so I can ask the question, what is the probability that you roll a 6? What is the probability that you roll a 10, 11, or 12? I can do that, okay, because I have some idealized probability mass function. Here's another probability mass function on this world where I'm not rolling 2 dice, but it's any situation where I have a binary outcome. I can call one of them a success. I know historically what the probability of success is, and I can wonder how many of those that I'm doing out of the n will be the success. If that's my setup, then I know there's some theoretical probability mass function that describes that outcome. And so we have many of these idealized theoretical probability mass functions that will describe the probability of something happening in real life. They are very, very useful to us. And so that's what statistics is about, to find the right model for what is happening. And we are going to do students' t-test, and we're going to use one of these theoretical models. And we're going to use Pearson's chi-square test, and we're going to do linear regression, and we're going to do analysis of variance. And they all have some idealized probability distribution, and we're going to use that thing to calculate the probability of this. Doing our study once, we found an outcome. How likely was that to find that outcome? Okay, that's all you have to take home for me. Okay, but so far, is everyone happy with the crucial bit of this idea of a total area of 1, and I can get some outcome of that thing? Everyone happy with that? Okay. I think that's enough of these distributions. By the way, I think I also did this little thing. So I have a probability of success here of, I vary the probability of success there, and I have 40 trials, and I want to know, I can't remember how many I wanted for that to happen. But can you see, as I change the probability of success, and that's just, instead of little bars, I just have little dots at the top of the bars. And you can see how this thing changes as I make the probability of success higher and lower. I think that's up to a probability of 50%. Yeah. Can you see that if I have a probability of success of 50% and I do 40 cases, what shall I find most often? How many successes should I find? Right in the middle, 20. That makes sense. But if my probability of success is lower, that little dot can just now show me for each one of those cases. So I'm asking only 4, I'm asking for 0, 1, 2, 3, 4, 5, and I'm visualizing all of them, all the possible. If I do 40 cases, I can have anything from 0 complications all the way to 40 complications. I cannot have 1.345, and I cannot have -2, and I cannot have 42, okay? So there's all my values from 0 to 40, and the heights of these is just the probability of the number of, for that specific number k. Okay, the value of that x can take. So by the way, here we'll just write the probability that x equals k. This is this thing. The probability mass function of this scenario, if this real world thing that I'm doing follows these rules, then I can use this theoretical model to determine what is the probability that x takes on a specific value. Okay, so many successes. And look again, the number of successes between 0 and 40 in that case is the random variable x. X can take on a value anywhere from 0 to 40 in this instance here. Is everyone cool with that? Okay, so I'm never going to ask you this one. This is too many things that you need to know before the end of the semester that I can contaminate the final exam by something like this. Okay, I need you just to feel that you understand. That you see, that you feel, yeah, that kind of makes sense. I might not remember it next week, but the thing that I will remember next week is the fact that the area of a rectangle is base times height. And somehow I can think of that as the probability of an outcome. Because not only can I do this, I can also visualize it. And I was just a bit lazy to make thin little lines, but I can think of each little line, because this is discrete, as the base being 1 and the height being so many out of 40. And so that I also have this idea that it all goes to 1. And if I combine all of them as 1, and I can look at each individual one, and that'll give me, the area of that little rectangle will give me the probability of that outcome. By the way, look here, if the probability of success is very low, it looks like here it's like less than 10% the probability of success. Can you see how unlikely it becomes to get this number of successes? Becomes very unlikely. But if I added all these probabilities, I've got to sum to 1. Okay, because that's everything that's possible. Now that's discrete random variables. Let's go on to something much more. This is cool stuff. If you ever get an opportunity to study discrete mathematics is a fantastic subject. And you can take courses in discrete mathematics. I don't know if they teach discrete math in the Department of Math here. I think every now and again they do have a course in discrete mathematics. And that's a beautiful, beautiful branch of mathematics. Okay. Forever the salesman, trying to entice you to go study take some interesting courses. Anyway, here we go. Let's talk about the continuous case now. Continuous. So now we have this random variable x, but now it is not stuck in the discrete world. I can now somehow roll a 3.4. Not only can I roll a 3.4, I can roll a 3.445768. Not only that, I can roll a 3. Can you see that I'll never end? I can just keep on adding decimal places. Or in front of the decimal point, I can add an infinite number of a billion, a trillion, a quintillion. I can never stop anywhere. And that's where we get the real number line. Remember in school, the real number line? The set of all real numbers. Okay. They are what we call an uncountable infinite set of values. You cannot count how many real numbers there are. Can you count how many natural numbers there are? Yeah, they are a countable infinite number of values. Okay, they are infinite. There's an infinite number of natural numbers, 1, 2, 3, 4, 5, 6, 7, but there's a one-to-one correspondence with the natural numbers itself. So I can count how many there are. How many integers are there? So whole numbers. So including the negative numbers. There's an infinite number of them, but are they countable? Yes, there is. Because I can say 1 and negative 1, I can give them the numbers 1 and 2. Negative 2 and negative 3, I can say that's number 3 and number 4. And so I can carry on. So even though there are an infinite number of them, and intuitively, you do feel that there's the infinities, there's different kinds of infinities, even though they're all infinite. Okay, those are countable infinite sets. But can you then imagine that the real numbers are uncountably infinite? I cannot count how many real numbers there are. Because it doesn't matter how many decimal places you give me, I can always add some more. And that's every decimal place I add is a new number. And so they are uncountably infinite. That's a very large infinity. And so you get even larger infinities than that. There are different sizes of infinities, even though infinite is infinite, isn't it? No, it's not so. Okay, but now I have a complication suddenly. Can I still draw rectangles? to say what is the probability that I get 3.147? Can I do that? So shake your head viciously, no, in the Western style of saying no. Okay, why not? Why can't I have a little rectangle like that? Because clearly now the rectangle no longer represents just the single value. And by the way, I think that's why I put those lines, just to say it's not truly that the base is 1, it's just this idea that it's discrete, so it can only take, that is one specific value. There's not, at 3, there's not 2,999, and there's not 3,0001, it's just 3. Okay. But what about 3.17? But what if I add just another 1 there? Is this now included or not in that little rectangle? And what if I add some more values? Is that now included in that little rectangle? It no longer is. So let's look at this idea of visualizing the distribution of x when x can be a continuous number. So how does a histogram work? So we already said it's these little bars, but now they touch each other. Whoa. And we do that because we want to visualize the fact that this is some continuum. Okay. And what we do is we very artificially decide on what we call the bins. And I'm going to say that that is 0, and let's just, stupid example, that's 10, that's 20, that's 30, that's 40. So I've just created these bins, cutoff values that if a number falls in that value between 0 and 10, it goes into this bin. If it falls between 10 and 20, it goes into that bin. And can you imagine a spreadsheet of people's, I don't know, their white blood cell count or their glucose level? I have all these values, okay? And it can be anywhere from, so let's imagine it's some blood value and it goes between 0 and 40. So how many people had a value on this little interval, 0 to 10? How many between 10 to, can you see that when I said how many people chose black as their favorite color, how many orange, I can just count how many blacks there were, how many oranges. When we rolled the die, I can count how many 2s were there, how many 3s were there, how many 4s were there, okay? And if I just divide by 36 or the sum total, it becomes a fraction, okay? So here I'm doing the same thing. Even though this thing is continuous, I'm just counting how many were between 0 and 10. And the heights of the bars can still be how many cases there were. So imagine this one was 55, and this one was 60, and this one was 57. I can do that. But imagine right at the end there were 200 cases, okay? I can still say, well, if there was 55 in that, I can say, what's the proportion? 55 over 200, which is? Okay? So instead of making this on the scale 0 to 55, I'm making this scale my proportion scale, which is? 0.275. Can you all see that? Okay, if I add all these bars now, what will they add up to? Base times height. They are going to sum to 1, aren't they? Everyone can see that. Okay. Now, though, I've got this thing that it's not base times height anymore, because that base is no longer just one single unit. This actually goes from 0 to 10. There's many possible values in there. Can you see that that's a problem? We can no longer make use of this idea of a discrete case. We better have some idea that there's some values in between 10 and 20. One person was 3.714. The other person was 5.694. The other person was 9.438. The other person was 0.0475. They all fell in this bucket. And it's a bin. I can count how many there were. I can divide by the sum total of people that there were. And so each of the heights is now a certain value. The proportion out of the 200. But I've got a complication here. 0 to 10. I've got a complication there. But now you say, well, that shouldn't be a complication. Why don't you make tinier little rectangles so that they each just 1? You know? And now I'm going to go, this 10 is now divided into 10 little things. 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you imagine? Okay, so there's 10 of them there. Now everyone is 1, 2, 3, 4, 5, 6, 7. Can you see that? Now there'll just be fewer cases in here because if I had 55, that 55 has got to be divvied up between these 10. Cool? Okay, but why stop there? Because I said I can just make it even smaller and smaller. I can just add more decimal places. Why do I stop it from 0 to 1, 1 to 2, 2 to 3? Why don't I go from 0 to a half, and from half to 1, and from 1 to 1.5? Why do I stop there? Why do I make it not smaller, and smaller, and smaller, and smaller? Can you see that? I can make it smaller and smaller, and there's no end to that. I can keep on shrinking. You give me a value, I can cut it in half and make it even smaller. You give me another value, I can cut it in half because I can just add more decimal places to it. Can you see that? So there's no end to me making these little bars thinner and thinner and thinner. Where will I end up with the base of this little rectangle? Where would I end up? What will the width be, the base be? In the end, it's going to be 0, isn't it? I mean, once I get to 0, there's no nothing. Can I ever get to 0? No. It's uncountably infinite. No matter what real number you give me, I can always cut it in half, and cut it in half, and cut it in half. I can never stop. I just cut it in half. Eventually, in practice, we will get to 0. This thing is 0. Does a little rectangle with a base of 0 have any kind of area? Base times height, 0 times anything is 0. So it loses its meaning. Any little value now loses its meaning because that little bar becomes so thin that its base is essentially 0. And 0 times anything is 0. So what do I do now? I lose the ability for x to take on a specific little value x. Can you see, I cannot ask, what is the probability that x equals 3.174? Can you see that that makes no sense? Because I would have had to go to a bar that is becoming a width of 0. Can you see in the extreme what will happen here? Because what is 3.147? Well, maybe the apparatus with which you measured this thing, next year they bring out a new model, and it doesn't just do 3.147, 3 decimal places. This new thing is more accurate. It'll now give us 4 decimal places. And 100 years from now, we'll get this machine that can go up to 10,000 decimal places. Okay, can you see that extreme? So would it have made sense to ask, what's the probability of 3.1474? Well, if I had more accuracy, maybe there was a 0, there was a 1, 0, 0, 0, 0, 0, 0, 0, and there was a 1 right out there, out in Baltimore somewhere. Can you see that? So I lose this ability to ask what the probability of 3.147 is. Because in essence, I'm dealing with a continuous possible values that x can take, and one specific value has lost all meaning. Okay, so I can no longer ask what's the probability that in a continuous random variable that the value is some specific value. I have lost that ability. Is everyone cool with that? Everyone happy with that? Cool? So now what do we do? What did I do with that red case where I said, that's how we roll the dice. What's the probability of rolling a 10 or more? What did I do? I colored 10, 11, and 12 in red. Did I not? So now, wouldn't that be possible? What do I do with the bars? Can I not say, what's the probability that x is less than or equal to 10? On my little bar, 0 to 10. Yes, I can. Now suddenly the base has meaning, doesn't it? It's not a specific single value. It is now a range of values. Just as I colored those bars in red, the 10, the 11, and the 12, and I asked, what's the probability of rolling a 10 or more? That's what we do here in the continuous case. We cannot ask what's the probability of a single value, but I can ask the probability that x is some range of values, some continuous range of values. I can't hop, skip, and jump around. I'm asking some continuous set of values. So now, wouldn't now just be this times that? Yeah, for sure it would. Because the base now has meaning. Can you see that? That's what we do in the continuous case. Can you all see that? Everyone who's not happy, just put your hand up. I can try and explain it in another way. It's, in essence, a very simple idea, isn't it? So when I have a discrete variable, I can say x equals some specific value. As long as it's within the bounds, if I do 40 cases, I can't have -3 successes or positive 49 successes if I only do 40. But it's individual numbers. Okay, here, I've lost that. I have to, because I can just make these bars smaller and smaller and smaller. So I have to do this kind of thing. What's the probability that x is between 10 and 20? Can you see I can do that? or 13 and 28. As long as they are together, that'll be some little section, and I can count how many fell in that section divided by how many I had. That makes sense now. Okay, we can do that. Now though, we fortunately also have, what did you say? Integral calculus. What did I ask you right in the beginning? What is the area of this shape? You could not answer that without calculus, couldn't you? Okay. But you can think of this as being infinite little rectangles, can't you? And can I not just ask you what is this area? It's going to be some fraction of the whole, isn't it? And what can I do? I can do integration, which we're not going to do, from, say, 0 to 10. The integral of 0 to 10 of this probability, now we're going to call it a probability density function. No longer probability mass. Mass is used for discrete. Probability density function. Okay, I'm going to integrate some probability density function. Now, first of all, we'll deal with very nice ones. In statistics, there are many continuous. But remember, these things are models of how the real world works. We've seen a model, a theoretical model, of how rolling two dice works. We've seen a model of how a set number, a finite number of Bernoulli trials works. Theoretically, that follows a binomial distribution. That's our model of that world. So let's model something that's much more interesting. This continuous world, and the one that we're going to start off with is the random variable is described by or follows a normal distribution, and the normal distribution is described by two parameters. Remember, my function had n and p in it, and n took on a specific value k, or x then took on a value k. Here's two parameters, mu and sigma, or let's put it sigma squared. Mean, variance. Remember variance from week 1, the standard deviation? So what does this distribution look like? Okay, we don't do infinite little bars anymore. Now we just have a line, okay? And you all know what this one looks like. Now, I don't do these very well. Surprise, surprise. But there's our bell-shaped curve, isn't it? That is, if I were to use a computer, and there's a certain function that I plot, it gives me this line. What does this function look like when I plot it? Can you remember from school? It looks like this, doesn't it? Parabola. With a extremum at 0.0. Cool? Remember that from school? There's a function that will draw this curve for me instead of this curve. Okay, and that function is a probability density function. The normal distribution has a probability density function. It's 1 over, now I mustn't get this one wrong, sigma 2 pi e, I'll tell what e is, minus x minus mu squared over sigma. If I plug that into a computer, if I plug in x squared, it's going to draw a parabola for me. If I plug in that formula, it's going to draw this curve for me. Can you see that it's just a function that draws a curve? Okay, but this is a probability density function. What's the total area under this curve? So we don't say the area of rectangles anymore. We just swap our words. We say it's now a continuum. It's no longer individual. If you do calculus, remember Riemann little rectangles? That's how we went from discrete to continuous in calculus. But let's imagine we've skipped that. We now have a continuous line that is now the probability density function. Just be careful. Imagine this value is 98. Can I say that x is, if this is all my possible values that x can take, can I say that this equals 0.0, 0.3? Imagine this was 0.3 on the y-axis. Can I say that? Is the top of this line now the probability that x equals 95? If I plug in 95 there, and it pops out 0.3, can I say that's the probability of x being 95? No. Remember we said it's a continuous numerical variable. There's no sense in asking what a specific value is. The only thing that I can ask is, what's the probability that it fell between those two? Okay, that I can ask. between 90 and 95? Can you see that I can ask that question? So please just remember that. We can't do that. We're always going to have some interval. All right. Just by the by, where does this thing ever meet the horizontal axis? No, it asymptotically approaches that 0, but it never touches it. And where does it go off to? Theoretically, this goes off to negative infinity, and this thing goes on to positive infinity. Okay. So it never ends. Okay. So typically what we would do is we'd say, what was the probability that it was less than 95? And by that we mean all until negative infinity. Even though negative infinity was not possible, if I ask you, what is everyone's height? And the height was described by this. The theoretical model of height in the world is described by this function. No one's going to be negative infinity height. Okay, but that's how these theoretical models work. We have to think about it going off to infinity. But what's this total area under the curve? Now, this is a beautiful mathematical thing. Human minds are phenomenal machines. They can come up with wonderful things. Even though this only asymptotically approaches this horizontal axis, there is still a total area under the curve. These things we call, they converge. So what is the total area under the curve of this? It's all possible outcomes. What's the total area under the curve? What was the area of all the little rectangles? 1. Okay. So anything that can possibly happen is under this curve, from positive infinity to negative infinity. Cool? I can no longer ask what's the probability of just one single value happening, but I can ask what was the probability that x was less than 95. So it's everything from negative infinity, theoretically, up till 95. Can you see that that is some area, a fraction of the whole? All possible values that x can take, okay? I'm asking for a proportion of that. Only the values 95 and less. Can you see that that's still an area? And didn't I just say in the beginning, if you understand what the area of a square is, or some geometric object, you can calculate probability. The same is happening here. Can you all see that? It's just that I'm in the continuous theoretical world. I can have an infinite number of values on the real axis, real number line. I can no longer ask the probability of a single value, but I can ask on some interval. Okay? And all we're saying here is less than 95. But can you see if I could calculate this proportion of the whole area under the curve, I still have the probability of randomly selecting someone from this distribution that has a value at most 95. Okay, so that was a bit quick. Let's do this one more time. I am imagining that there's some process in the real world, and this thing is governed by, just as rolling 2 dice is determined by this theoretical distribution of 2 dice rolling. There's some process in the world that determines people's height. Now imagine this is some alien planet, and the distribution of people's height is normally distributed. And I knew there's 10 billion beings on this planet, and we knew the height of every one of these aliens, all of them, okay? And we can calculate a mean. You can all calculate that from week 1, no problem. And I say, is it a population or just a sample of the population? It's the whole population. So we're going to say mu equals, and let's make it these beings are 100 inches tall, okay? And they have a standard deviation of 10. We absolutely knew this of all 10 billion of these little aliens. And we say there's a theoretical distribution of their heights that determines the value of them. And we're going to say, it just so turns out beautifully, as by some freak of nature, those heights follow a normal distribution. Okay, so we're going to say the heights of these aliens, any one alien has, if I take an alien at random, they're going to be a certain height, okay? And say this random variable is described by or follows a normal distribution on a mu of 100 and a variance of 10 squared. Can you see that? Okay. If I plugged in these values into that equation, what's going to happen? My computer software is going to draw a nice little curve for me, and it's going to look like this. Where am I going to find, so we can think of this, what's the area under the curve? All possible heights, okay, is 1, okay. Where am I going to find most people? I'm going to find them, I said, their height is governed by this theoretical function, the normal distribution on those parameters. Most people are going to be, how many inches tall? 100 inches tall. That is where I'm going to find more people. I'm going to find more people around 100, not specifically 100, that loses meaning, but most people are going to be around 100. And say 10, so maybe that's 90, maybe that's 110, maybe that's 80, maybe that's 120 inches. Can you see that as they get shorter and shorter and shorter, it's less and less likely that people are that height? And taller and taller and taller, I'm going to find few and few and few of those people. Is that cool? So I can say that this group of aliens, their heights is under the control of this theoretical probability distribution, which turns out to be the normal distribution on these two specific parameters. Can you see that I can now ask the following questions? I can ask, what is the probability, and everyone should answer this one. What is the probability that a randomly selected individual from this alien planet is 100 inches tall or less? That is at most 100 inches tall. What's the probability of finding that? 50%. Who shouted out? 50%. Who shouted? We shouted out 50%. There you go. There you go. Is anyone in disagreement of that fact? Okay, total area under the curve, 1. What is the probability of selecting a random individual from this population that is at most, I cannot ask, that is 94.5789 inches tall. I've lost that possibility because the finer I measure there, now you go to the height of a cell on the top of their head, and then the layer of the cell wall, and now the layer of, I'll never end. Just depending on how accurate my measurement is, that decimal place will never end. Okay, I've lost that ability. Okay, but I can ask the question, what is the probability? If this thing is symmetric, it is symmetric by the way, so I can draw a line straight up there, this side looks just like that side, okay? What is the probability that I find a random individual that is at most 100 inches? 50%. What is the probability that that a randomly selected alien from this planet is at least 100 inches? Yeah, and the value? Yeah, what I'm asking you, now we remember our discussion of the circle and the triangle and the rectangle. I'm asking you, what is this area under the curve? What proportion of the whole, I said at least 100. So it can be, this alien can be 5 light years tall. It's quite possible. You see that? Okay. Highly unlikely, but theoretically not impossible. Practically, yeah, very impossible. But can you see it's a fraction of the area under the curve? Okay. Now, what would I have to do to this function? I would have to integrate it from 100 to infinity, wouldn't I? I have to take that integration because when the curves start looking not so nice anymore, I don't have a formula for it anymore. And you all told me I have to go to integral calculus. Now, fortunately, we will not have to. Now, there's a very special version of this normal distribution called the standard normal distribution. You all know that one. What is the mean of the standard normal distribution? Let's put an N, but let's put that it's NSTD, standard distribution. What are the parameter values for the standard normal distribution? What is mu? 0. What is sigma, or sigma squared? 1. Okay. So it has a mean of 0, and it has a standard deviation of 1. Okay, so there we go. Most people will be about 0. They'll be -1, they'll be +1, they'll be -2, they'll be 2, they'll be -3, they'll be 3. Okay, same thing. Okay, it's just going to be around 0 and symmetrically on both sides. That's called the standard normal distribution. Now, there's days way before we all had the computing power in our pockets to land and something on the moon. People had to do this by hand. There was calculations by hand. There were tables, okay? Not all functions can be integrated. Not all functions can be integrated using this symbolic form. Okay, we have numerical approximations for some of these. Okay, functions are not always as behaved as y equals x squared. By the way, what's the integral of x squared with respect to x? Can you remember how to do that? Indefinite integral, that would be a, say it? No, that would be its derivative. What's its integral? It's antiderivative. Can you remember? No one can remember? A third x cubed plus c, remember that from school? It's a well-behaved function. I can do this exactly like this. But if it's very bad, I have to use numerical approximations. That's how most functions are, the area under the curve is calculated. But so happens that people put a lot of effort into this one. And people know, you give me a value here, negative 1.4, which is right there. You give me a value, I can tell you from a table what this is. I don't have to use integral calculus. Someone put in that hard work by hand over many, many years. And we have these tables that can do that for us. But that's not how real life works. Real life says, well, the mean is not 0, and the standard deviation or variance is not 1, because 1 squared is also 1, so standard deviation variance in that instance is the same. But it's a 110. Can you see that? That's real world. Now, do you think for every possible value that this thing can take and every possible value that that one can take, someone over the course of history sat down and worked out tables for all of them? For 100, and 100.004, and 100.00007. No one's done that. It's impossible to do that. Okay, so no one did that, but people do have this. People have worked out this table. So you can give them any value here, and they'll tell you what the area under the curve is. Okay, there's tables for that, and the old version of this course still asks you to go look up a table. No. We have technology for this, okay? So no one's going to ask you that. But we do have this, okay? Someone does know this, but you're just going to use Excel to do that for you. If you want to use R or Python, you're welcome, but that's the spreadsheet I gave you. It'll just calculate this area for you. You plug in a value, it's going to tell you this area under the curve, okay? Fortunately now with our computers, you can have any one. It'll still tell you the area under the curve, but it comes from the historical time where we only had this one. Okay, the 0 and 1 special one. Now I'm asking a quick question. Can I move from this, I'm going to call it world, can I move from this world to this world? Okay. If this thing was described by a mean of 100 and a variance of 10 squared, this one, can I change any possible value that this x can take from this world to this world? Turns out, yes, there's a very simple calculation to do this. Okay? And now we don't call it x anymore for reasons that we won't go into. We call this thing z now. And we say z is described by the normal distribution with a mean of 0 and a variance of 1. Okay? And I can go from this world to this world. So no matter what the real life situation you give me, I can always go to this world. And because now it's very easy for me to calculate areas under the curve, because someone did it on paper before in little tables, big tables. Now I can just use a computer to do it anyway. But we're still stuck with this thing. And there's a very easy calculation. So this one you must absolutely know. I say I take x minus mu divide by sigma. And I'm saying that's z. You give me any value x. I know what mu and sigma is. That was 110 squared. So I know that value and I know that value. So you give me any value in my data set. I will subtract mu from it. I'll divide by sigma. And I'll go from this world to this world. So 110 minus 100 would be 10. Cool. 10 divided by 10 is 1. So 110, if someone was 110 there, there'll be 1 here. Same thing. So any value here can be transformed into a value on this axis by this simple little formula. Can you see that? Okay, now that you can see that, let's put it into action. I am now going to ask you the question. I have a data set, and I think that this thing that I'm measuring in these people is governed by a theoretical distribution. The values that I can randomly get from my random experiment is governed by the normal distribution on, so x is described by a normal distribution, and let's keep it like this, 100 and another 100. So the standard deviation is 10 and the mean is 100, making the variance also 100. Cool? And I'm now asking you, what is the probability that a randomly selected person is at most 95 inches, or whatever that thing is I'm measuring? Is that a valid question? Yes? Okay, I'm not saying x equals 95. By the way, can I also say that, less than or equal to? Yes, I can. Okay, because these things are at an infinity. So less than or equal to, no difference.
Do we have to square the mu, or are we just taking it?
So some people write the standard deviation there, some people write the variance there. The value that's in our little calculation, though, is the standard deviation, not the variance. So just be careful. Be careful how I write this. I will not try and trick you. I will say when I say that, when I write there. Some people write the standard deviation there, but it's more common to write the variance there. Okay? But I will tell you that so that you know you plug in. If I say that the variance is 99, or let's make it 9, the variance is 9, what are you going to plug in there? The square root of 9, which is 3. Okay, so it's much more common that people put variance there, but some textbooks do put standard deviation there, just because we're going to plug in standard deviation there as well. Don't plug in the variance there. Okay, but I won't trick you like this. All right, cool. Can I legitimately ask that question? Yes. Can you see that if this thing that I'm measuring is theoretically controlled by this probability density function, that this is what I'm looking at? Can you see that I am asking 95, there's 95. Can you all see that I'm asking this area under the curve? Can you see that's what I'm asking? Is everyone happy with that? Probability is proportion of a whole. That's all possible outcomes. I'm asking less than 95 on this side. So in essence, I would do an integral from negative infinity to 95, and I'll get the solution. Okay, we don't have to do that. So let's see if we can change that to the z world. Let's call it the z world, because that's much easier for us to work with. This one's much easier to work with than this one. Okay? Now remember from school, if I had an equation and I said x plus y equals 35, okay? And I have an equality. What I do on the left-hand side, I have to do to the right-hand side, otherwise I lose that inequality. Remember that? But that equality. But the same goes for inequalities as well. To maintain that inequality, I have to do on the one side what I do on the other side. So let's do that. I say probability that x is less than or equal to 95. I'm just giving myself a bit more space. So what I do on the left-hand side, I've got to do on the right-hand side. What do? I subtract mu, don't I? Minus mu, but if I subtract mu on this side, I better do it on that side too. Minus mu. What do? I divide by sigma. I divide by sigma. What I have to do on this side? Divide by sigma. Everyone see that? What I've done on the left-hand side, I do on the right-hand side. These are positive values. I'm dividing by a positive value. So I know sigma is always non-negative, and it can't be 0. Otherwise, I won't have any distribution. There'll be no spread in this data. Okay, I have to have some spread in the data. Okay, so what I've done on the left-hand side, I've done on the right-hand side. These are positive values, so I don't have to swap the sign. Happy? Okay. What is this thing? It's z. Huh? So I'm just going to say probability that z is less than or equal to, what is 95 minus 100 divided by 10? Someone tell me quickly. Negative 5 over 10, negative a half? Is that what we're asking? Yeah, so I'm asking, what is the probability that z is less than or equal to negative a half? Is my math right there? My arithmetic. Sorry. Okay. Can you see that these two questions are exactly the same question? I've just transformed from x to z. Okay? So now instead of being at 95, can you see I'm at negative a half? Can you see that? So what I'm really asking is this area under the curve. That would be the same thing as asking, what is this area under the curve? Can you all see that? There's a frown. And then a smile. Okay, is everyone happy? Can you see that? Why am I doing this? Because I know the answer to this. I can find it in a table, or actually the calculation is much easier. Even if I wanted to do integral calculus, what happens to mu? What is mu? 0. What is sigma? It's 1. It's 1. Now the calculation is much easier. It is 1 over square root of 2 pi e to the power negative x squared. That's a much simpler equation. I can integrate that thing. Whereas if I had to plug in values into the full one, which is not 0 and 1, 100 and put a 10 there, that's much more complicated. Okay, so it's much easier to calculate areas under the curve for this one. But here is the crucial thing. Can you see that if I say all possible values that some variable can take, okay, if theoretically these values are described by some function, some probability distribution, the probability that the intervals of values can take, I can solve that problem by having the function, the area under the curve is always 1, and I'm just asking you for some proportion of 1. Can you see that that's probability? Can you all see that? If this thing that I'm measuring in this population is under the control of this theoretical distribution, I know the function, I know what it looks like, I wrote down the normal distribution there. It is going to give me a curve if I use the computer, just like x squared gives me a parabola. It's going to give me this beautiful thing. Turns out, beautiful human mind came up with this. There's a bell-shaped curve. Who came up with the fact that there's a pi in there? Pi is about circles. How does this thing have pi in it? Isn't that, that's beautiful. Not only does it have the transcendental number pi in there, or the irrational number pi, it also has the irrational number e in there. Who knows what e is? Euler's number, 2.7 something, something, something. Also an irrational number. It has a bunch of irrationals, so it has this bunch of decimal places that never end, just like pi has decimal places that never end. How does pi and e get into an equation that draws a beautiful symmetrical curve that has, by integral calculus, a total area under it of 1? Isn't that beautiful? I mean, you've got to take your hat off to people who came up with that. That is a thing of beauty. That is brilliant, okay? And it doesn't just fall out of heaven. There's a whole history behind, and you can look at videos how that derivation came about, okay? You can watch it in 5 minutes. It took people a lot longer than 5 minutes to figure that out. But we have it, and that's what it looks like. It's very nice. So let's have a look at some of them. And then we'll end there today. So there's the normal distribution. That's on 0 and 1. But I did this. So obviously, if I change the mean, what happens to the curve? It just goes left and right. I'm just changing the mean. Everyone can see that. And the spread, the standard deviation or variance, if I spread it out, that's a bigger variance. If I make the variance or the standard deviation smaller, it's less spread. So those two parameters absolutely determine the shape of this bell-shaped curve. So that's why they say the normal distribution is completely determined by those two parameters. You give me n, you give me mu and sigma, it'll draw that curve for me. But no matter what I make sigma, and no matter what I make these two things, the area under that curve is always 1. That's the beauty of the normal distribution function. If I integrate from negative infinity to positive infinity, what is the answer going to be? 1. The area under the curve is always 1. But I'm always going to ask you some proportion of the area under the curve. Okay, so here comes 3 things that can ask you. I can ask you, what is the probability that x is less than or equals some little x? X is my random variable, all the possible values. This was height of aliens, but whatever this thing is that I'm measuring, I can ask you, what's the probability that x is less than some specific value? And in this instance, we said 95. What's the probability that x is less than 95? Can you see that I could also have asked you, what's the probability that x is at least some value? Okay, let's just draw this out because we have got to look at this. This thing is weird. This thing is weird. There's my probability, there's my function, and you give me mu and sigma, it draws the specific one. That's 100, that's 110, that's 90, that's 120, that's 80. And I ask you, what's the probability that x is at least 110? Can you all agree this is what I'm asking you? Can everyone see that? X is at least 110. It's the proportion of those aliens that are 110 or more. I cannot ask what's the probability of the aliens being 110 inches high. I've lost that ability. I've got to have some interval. So the 110 or more, can you see that that's this proportion of the area under the curve? Now I have a problem. Now I have a problem. Now, who didn't have calculus? Who didn't do integration? Okay, so by the way, when you do an integral, we go from this number to that number. That's how we write it. And we always have a lower bound and an upper bound, so that this value is smaller than that value. Okay. Now, what that happens is, if the bottom one is smaller than the top one, it means I'm always going to come from this side to some specific cutoff. I'm going from a lower value to a higher value. Can you see that? If A is always less than B, I'm going from lower to higher. So integral calculus is always going to give us an area under the curve. This lower bound is always going to be negative infinity, because I'm saying at most 90, at most 100. So it's from negative infinity till 90. Negative infinity is smaller than 90. So my area under the curve is always going to be from this side. I can only ever calculate area under the curve from the negative infinity side, from integral calculus. Okay? Now, how on earth will I calculate that area under the curve? What am I going to do? What am I to do? The answer is in plain sight here. Come up with a suggestion. Solve the little problem. Yeah. Didn't we say that if I have two possible outcomes, either people fall there or they fall there. The aliens are going to fall there or there. Isn't the probability of A complement 1 minus the probability of A? Yeah. So can I calculate this area under the curve? Yes, I can. And if I subtract it from 1, what have I got left? That side. So if I asked you what's the probability of at least, so I'm asking you that side, you've always got to be doing 1 minus the other side, the lower side. You always have to do that. So if I were to ask you a question, which you are going to get for the labs, I'm going to ask you, what is the probability that, in this instance, x is larger than or equal to 110? Well, let's make it 110. What have you got to calculate? You have got to change this to say it's 1 minus the probability that x is less than or equal to 110. Can you see that? Can everyone see that? Okay, speak now or forever hold your peace. You promise me, you know what, you can see this, okay? It's clear. Happy? The backbench is happy? Not happy? Okay, let me go through it again. Thank you for saying that. I want everyone to be on board. As I said, everything is about an area. We started with the area of a square and then the area of a rectangle. This is also an area. Cool? The total area under this curve, the total area of this shape is 1. And I'm just asking for some proportion of that. That's going to be my p-value. Eventually, it's going to be a p-value. What was the likelihood or the probability of your study having this result? You're going to say p is 0.04. Hey, significant result. Guess what? That's going to mean you got one of the unlikely ones. We'll see that happen. Okay. But because this is all based on integral calculus, and integration is going to be done from a lower value to a upper value, I'm not doing the complication where I can swap those around, but then I've got to put a minus there. That'll also work. Okay, but that's calculus, and this is not a course in calculus. So we're going to stick to the simple case. This number is always got to be lower than that number. So I'm always going to say I'm going from negative infinity to some number, b. So I'm always going to be able to calculate only from there to some value b. So no matter what b is, it'll always be on this side. But that's not what I asked you. I asked you what's the probability of 110 or more. You cannot calculate that. You cannot do that. You can, but that's not calculus. The going from, you can do from, here would be infinity to 110. But can you see infinity is bigger than 110? Okay, we can't do that. We said that the lower one must be lower. So we are always calculating from this side, area under the curve on this side. But now I've asked you that area under the curve. And all you do now is you say, well, I'm going to draw this line there still. I know I can only calculate this area under the curve. So do that and subtract it from the whole. And if I subtract the whole minus this bit, what am I left with? That bit. Cool. So whenever I give you this problem, immediately swap it around to this problem. So you swap that sign around and you say it's 1 minus this area. Cool. Yeah.
What happens if your z-score is 0?
Hmm?
If your z value is 0?
Now, can you calculate the probability of exactly a single value? No. So what interval are we talking about? You cannot ask, what is the probability that z equals 0? Okay, we can no longer have 0.
If you were to have 110 as your value and plug it into this thing on your left, right?
So where do you want me to plug in this value?
The 110 into the x minus mu over sigma.
So 110 minus mu divided by sigma. That's 10 divided by 10, that's 1.
But then you have to do 1 minus.
No. Why is that not so? Think it through.
Like, for the second.
I cannot do that. So where will you end up with a value of 0? What would give me a value of 0? If I asked you the question, what was the probability that x is at most 100? 100 minus 100 is 0. Divided by anything is 0. Okay. But what am I asking? If I translated that into the z world, what am I asking? So this is less than. So let's make it easy. So let's listen to a question because it's a very valid question. And if you get that, that's a good indication that you understand what's going on here. I said, what is the probability? Now let's make it the uppercase because you're interested in uppercase. What's the probability that x is at least 100? What's the answer? You can just shout it out. What's the answer? Think of these aliens. It's half, isn't it? So you know we're not going to get to 0. We're going to get to a half. So how do we get to a half? Okay. We know that we can't calculate this. Why? Because I cannot calculate this area under the curve. I can only calculate from this side. So I'm going to calculate this side and subtract it from 1. 1 minus this equals what is left. Cool. So immediately I'm going to write 1 minus the probability that x is less than or equal to 100. You see where this is going. Okay? So that equals 1 minus the probability x less than or equal to 100. I subtract mu. What is mu? 100. I divide by sigma. What is sigma? 10. 1 minus the probability, this is all z, is less than or equal to 0. Guess what? If I have the standard normal distribution on 0, 50%. 1 minus 50 is 50. Cool question. Here you can see. You're never going to get 0. Okay. Everyone happy with that? So I can ask you this thing. What is the probability of less than? What's the probability more than? But I can also be very nasty, which I will not do because it's not realistic in statistics, but it is in some textbooks. Okay, but I think it's silly to do. But so I'll just tell you about it, okay? Because I think there are questions of this in the lab. So I want you just to be able to figure it out. But I will never ask you that in the exam. I can ask you, so let's just draw a nice, new, fresh distribution. And I want to see if you can solve my last little problem. That it was this distribution of a mean of 100, okay? And I ask you, what's the probability that a randomly selected individual from this alien planet will have a height between 99 and 107? Still an interval. I can still do that. Because I asked from negative infinity to a certain value. I asked from a certain value to positive infinity. We can all do that. But what if I asked you this? How would you calculate that? So I've got this one. Okay, before you say, because you're right, just put your hand up. Do you think you can figure out a way to calculate this area under the curve? that proportion of a whole. Everyone feel happy that they can. Who thinks that they cannot solve that problem? Oh, no one's going to put their hand up to that one. Duh. Okay, so the solution is? So what he's suggesting is the following. Here we go again. Probability that x is less than or equal to 107. So what he's calculating at the moment is all this, oh, I don't want to do that one, is all of this. Okay? So you're going to calculate all of that. You can, because it's from negative infinity to 107, and then you're going to subtract from that the probability that x is less than or equal to 99, which is now, oh, let's do another color. So he's got that whole green thing, and now he's got this pink bit, and he's subtracting that whole lot from this whole lot, and it's only that bit that remains. Can everyone see that? Okay, we don't do that in statistics. I never ask you to calculate that probability. That's not how, that never comes up. Never say never, but that never comes up. But you could all see that, you could figure that out as a solution. Calculate this whole area, then subtract from that this area, and what remains is that area. Okay, can you see that? All right, I won't ask you to do. It is in the labs, I'm pretty sure. Remember, I wrote the labs a while ago. I can't remember every question in the labs. Okay, so you can figure it out. The thing is that I want you to do is to always realize that you've got to swap this over to a less than, because we cannot calculate more than. If we have to calculate more than, we swap it with minus the less than. Everyone happy with that? So let's look at the spreadsheet so that you can all see how that works. Have I got it open? Yes, I do. So this spreadsheet I send you, we will play with it this week, maybe a little bit next week. But in reality, for the rest of stats, when we start doing students' t-test and we carry on to the end of the semester, you're going to use a different one, because this is not realistic. Why is this situation not realistic? What did I say about these aliens and their heights? I knew the height of every single one. The whole population I knew the values of. Therefore, I knew the standard deviation or variance of each and every single human being. Is that realistic? You're going to put 100 people in your study, 200 people in your study. Do you know what mu and sigma is? The population mean and the population variance. You don't know that. You're going to know this group of people in your study. You'll know their mean and their variance. That's very different from knowing what the population is. So while this is all very nice and it helps us understand, it's not very realistic. Okay, so I'm going to, later on we'll see, I'll give you the spreadsheet with a realistic view of this. Please note that there are two tabs, two sheets under here. There's variable, and then there's this thing we'll discuss next week. So make pretty sure that you're on this one that says variable. And so there's an easy way for you to do that z calculation. If I say to you the variable value is 92, and the mean is 1, you plug in 92 there, you plug in 100 there, and you plug in the population standard deviation, not the variance, and out pops the z value. Can you see that that's 92 minus 100 divided by 6? Gives you negative 1.33. Okay, so instead of you having to do z equals mu, x minus mu divided by sigma, I've just put it there for you. But you can see that's all I'm doing there. Okay. Now here comes the 3 questions. Now what do I want you to do for the labs next week when these questions are asked? I want you for once in your life to write down the whole thing. Start with, I asked you p of x being less than or equal to 92. Minus x minus mu minus mu. Divide by sigma. Plug the values in for mu and sigma. And eventually write the probability that z is less than negative 1/3. So you've gone from 92 to negative 1.33. Do you see what I'm asking you? Okay? So do that by hand, and then instead of using your calculator, just come here and do it. In the exam, I will not ask you to write out all of that, but I need you to do it once or twice in your life. Write out the whole thing by hand. Okay? Shall I be clear about what I'm asking? Or must I show it? Hands up? Or are you clear what I'm asking you to do by hand? Everyone's clear. So you just write out that whole thing on paper. And then you can just use this as a calculator. In the final exam, you don't have to write everything out on hand. You can just write the answer straight from here. Real life. Real life is not writing that whole thing out. No. Okay. So there, please have a look at that. At most, at least, between. Between, you're going to do for me in the labs, and then never again. Yeah, in the other labs, they'll come up again because students T, we're going to do it again and again. In the exam, never, because that's not the question that we ask in real life. Okay? So there, I'm going to say, if I ask you the question, what is the probability that a randomly selected value from this population that is described by the theoretical normal distribution with a mean of 100 and a standard deviation of 6, what is the probability that a random value is at most 92? Then you're going to do that top one. Okay, so you plug in the 92, you plug in mu, you plug in sigma, out pops the z value, negative 1.33, out pops the probability of up to z, and you can see now why I call it up to z. It's from negative infinity up to that negative 1.33. Out pops the probability 0.09, and I put that little thing in because no one wants to write out 15 decimal places to the solution. Put in how many decimal places, you're free to choose. 2 or 3 decimal places is fine, okay? And it'll just do the automatic rounding off for you, so don't make a rounding off error. I'm very kind, am I not? Huh? I'm a kind person. Oh, it doesn't seem like people agree. I am. Okay, and there's the one at least. So you know that's going to be the upper one, which you cannot calculate. On paper, you're going to write for me 1 minus that bound. So you do that on paper, but then you can just plug it in. I'm asking, what is the probability of a randomly selected person if the values are governed by a normal distribution on a mean of 100 and a standard deviation of, what did I have there, 6? So variance of 36. You plug in that value, it'll calculate z for you automatically, which is 1 2/3. It'll tell you the probability that upper area under the curve from 110 upwards, okay? And then finally, you can do the rounding, and there's the nasty one where I say it's between that one and that one. So just check in your calculator if your hand thing, now you only get to z. Your calculator will not calculate the p for you. Why do you need software to do that? Or a table, an old-fashioned table at the back of an old-fashioned statistics textbook? Because you have to do this integral. Okay, and this is not a course in calculus. I'm not going to ask you to do that integral. So R and Python and all these things just do that for you on your behalf. Excel does it for you on your behalf. Out pops those p-values. And you can say that. So you can now answer the question, if this real-world thing that you're working on is governed theoretically by this model, okay, this equation, then, just as with the dice, if you roll 2 dice, it can land on anything, can it not, between 2 and 12. But theoretically, there should be a certain probability that it's 10, 11, and 12, 10 or more. Okay, is she going to roll a 3? For sure. You know, unlikely to be a 10, 11, or 12. It can be a 10, 11, or 12. Theoretically, I can say what is going to happen. The probability that it's going to be a 10, 11, or 12 is going to be so much. I can put a value on that. What happens really in that one roll of the die, you know, but we are saying there is a model of the world that governs the outcome of a random variable. What is the outcome? That I get a value from negative infinity to 92. If that random variable is governed by this theoretical model, then probably this is what I will find. Can you see that? This is a model of the world. And you will now, from now on, hear me say this thing very often. All models are wrong. Some of them are just useful. And that's how we do stats. We have these useful distributions. Okay, but they are all wrong. But some of them are just so wrong, they don't help us at all. But if we choose correctly, it's close enough to how it really is, that model becomes useful to us. So we're just imagining these aliens. I can now answer the question, if these are indeed aliens on this planet, and I know the mean of their height is 100 inches with a standard deviation of 6, I know what proportion of them, under these theoretical conditions, should be at most 92. What proportion of them? 9% of them will be at most 92 inches, if their height is governed by that model. Can you see that? That's what question I'm asking. The proportion of the whole is the same thing as asking, what's the probability of me selecting a random alien from their population and their height is at most 92. Can you see that's the same as asking what proportion of them are less than 92? The fraction of the area under the curve. Tell me you all get what I'm talking about. If you understand that everything we do from now on will be a curve, and we'll just calculate the probability under that curve from somewhere till some point. And that's a p-value, a probability of something happening. I can now always calculate the probability. And now you're going to do a randomized trial. You give someone a placebo drug, you get them a new drug. You're going to find some outcome. And now I can ask, what's the probability that I got this outcome doing my randomized trial just once? Guess what? If we could do this trial an infinite number of times, what are we going to find? Possible values that it could take. Where is your trial going to fall? Somewhere. And I can ask the question, what was the probability of your trial, or more extreme is usually the words we want? It's going to be a little area under a curve. We just have to do that in the next 2 weeks, where we can say, how do we think about doing an experiment an infinite number of times? We've got to come up with that. That's also going to be a function that draws a curve for us, which is going to be very beautiful. And our study is just one on there, and we can ask the statistics, p-values, is all this what I told you today. If you get today, you understand statistics, done. So just make sure before next week, in this week, contact your TA, contact me, and make sure you understand what I talked about today. If you get what I talked about today, you understand statistics like you've never understood it before. Okay, does this gel with your previous experience of studying statistics? For you that can remember that, does this make sense? Okay, it's very easy if you think about it this way, isn't it? Then if you just stayed at the equations, of course, that can sometimes be a little bit tough. If you view it in this sense, it is very easy. Do you agree? Who doesn't agree with me? Ooh, I'm worried now. Okay. Can you start getting the sense that stats is easy? You start getting that sense, that feeling. It's a very intuitive thing. And we're just going to, add more and more scenarios. Because not everything follows a normal distribution. Some things follow another distribution. But we're going to stick with the same story that we stuck with today. Okay, questions, comments, concerns? Yeah.
I was wondering, giving that example, the mean is 100, and the chance of getting that anyone between before that 100, so it was like 50% of chances. So rather than making a complex formula,
Yes.
why don't we just make it percentages?
Yes, you're quite willing to do that. So the beauty, some of what you're asking is locked inside of this beauty. Of course, this thing is symmetrical, is it not? So what one side looks like is the other side. So if one thing that's probably locked in your answer, if I asked you what's the probability, say for instance this was 100. This thing is symmetrical. If I asked you what is the probability of being at most 110, because this thing is symmetrical, is that not the same as asking you what's the probability of less than 90? Can you see that's exactly the same thing? That proportion, if this was 90 and that was 100, there's a 10 difference, there's a 10 difference. This thing is symmetric, mirror image. Can you see that that proportion is exactly equal to that proportion? And I could just have calculated up till 90 and I would have gotten the same proportion. Can you all see that? So don't worry about it, it's just fun facts. But I don't want you to get confused by this. Okay. There's an even better way of going about it. Let me show you that. There's a rule of thumb called Chebyshev, and now I can never pronounce that name. Okay, a mathematician, he worked out this rule of thumb. And he said that within one standard deviation, so let's go, we transform this into the Z world, so that this is 0, there's 1, there's 1. There's -2, -1, 1, 2. Can you see that because I divided by standard deviation, this would be the mean, this would be 1 standard deviation lower than the mean, this would be 2 standard deviations lower than, it's units of standard deviation. If I say you run 10 miles in 1.5 hours, if I divide by 1.5 hours, I get so many miles per hour. If I divide by standard deviation, I get so many per standard deviation. If I divide by standard deviation. So it's 1 standard deviation away from the mean, 2 standard deviations away from the mean. Okay, and he had this rule of thumb that says, within 1 standard deviation away from the mean, I will find 68% or 0.68 of the area under the curve. Rule of thumb for the standard normal distribution. Between -2 and 2, so within 2 standard deviations of the mean, I will find 95% of the area under the curve, which means, what is this area under the curve here? Okay, just do that one for me, come on. If, rule of thumb, this is 95% of the area under the, this is 95% of the area under the curve, what is this little area under the curve? What is more than 2 standard deviations less than the mean? What is this little area under the curve? If this is 95%, what remains? 5%. And I have to divvy up 5% on each side. So what's that? 2.5, okay. 2.5%, can you all see that? And then within 3 standard deviations of the mean, you find 99.7% or 0.997 of the area under the curve. So that's just a little rule of thumb. Okay, but I'm not going to ask you something that falls exactly on -2 or -1. That's a bit cheating. Okay, but if I did, if your z fell in one of these things, -1, you know, if this is 68% of the area under the curve, what is left? 32. Half of 32 is 16. Guess what? What's this area under the curve? 0.16. Okay, there's that rule of thumb. But it's an approximation. It's not exactly 68%. It's not exactly 99.5. It's not 95. It's not exactly 99.7. It's approximately, so don't use it. Okay. But yeah, is that some of the stuff you were asking about? Yeah, okay. So you can use that symmetry rule for sure. Why don't I like it? Because the next distribution we're going to talk about is the x-squared distribution, and it is not symmetrical. And then we're going to talk about the f distribution, and it is not symmetrical. Okay, so we lose that completely. So I don't like those specifically, but it does work in the instance of the normal distribution, and then the t distribution. It does work in those circumstances, but nowhere else. Okay, cool, is everyone happy? Come on, tell me that some of this is at least exciting. Has your needle on liking statistics moved a little bit? Oh, I see that shake of the head. I am so hurt now. Oh, the pain in my chest. Oh. Someone moved the needle a bit. Just say yes, someone, please. Yeah, okay. What's the time? Oh, is the TAs waiting? Did I go overboard? You have to stop me.
Okay.